And I guess we'll go ahead and get started with it. So, today is all about forces. So far, the first 2.5 weeks have been all about talking about how things move. Position, velocity, acceleration, splitting that up into multiple directions, doing all sorts of wacky things with it as we want to. All of that totally fine, but it's only talking about how things move. It's not talking about why they move, which is a little bit of a different thing. So if you've actually gone through the reading and if you looked at some of those things, you'll see there's a variety of different forces that might be acting, but a force is essentially some sort of push or pull that is going to try to change the movement of an object. Let's talk about what they do. Generally speaking, forces cause accelerations. If you have an acceleration, it's because of forces. It's inversely proportional to mass. So this thing is kind of a rearranged version, still on the eraser, I was going to say, this thing is kind of a rearranged version of Newton's second law. Newton's second law is specifically F is equal to ma, what we've got down here. But let's kind of pull that back. Let's pull it to something a little bit more, maybe closer to home. Say your car breaks down, and you've got some friends that are helping you push this thing. Which car would be easier to push? The 2-door, 2-seat smart car, or the 4x4 truck that's got doubled up tires in the back? Which would be easier to push? Which one would be easier to move to wherever? Probably the smart car, right? I would agree with that. And I don't even know if you guys know what smart cars are. They were barely on the road they were only around for a little while. Smart cars were incredibly tiny cars that looked like they were made out of like cardboard or something, right? They were incredibly small. They were supposed to be very high fuel efficiency, very little mass, which makes them easier to move. It takes less force to move a less massive object. The massive truck has a ton of mass, right? That's why we call it massive. It's got a lot of mass. So when we're pushing it, we can apply the same amount of force to the truck as we did the smart car, but the fact that there's so much more mass means we're going to get so much less acceleration because they're inversely proportional with each other. The same force, but more mass means less acceleration. And Teslas still kind of fall into the middle because I know they are a little bit lighter, but they've still got those batteries and a lot of other components inside of them. Like the smart cars, as I'm talking about them, were tiny cars. I don't think they make them anymore. But we can imagine here that it's not just going to be us pushing our broke down car. There's going to be a lot of different forces that might be acting on things. There could be friction. There could be tension. There could be our anti-gravity guns. There could be electric and magnetic forces. There could be normal forces, gravity, dark matter, any forces that we could possibly imagine acting on an object all at once. And still, we can characterize it with our good friends, the kinematic equations. And why is that? Well, when we're actually doing these things, we don't actually have to consider every single individual force. Not at least like that per equation. What we can do is we can instead work with what we call the net force. If I take every single force 1, force 2, force 3, 4, 5, 6, however many forces we have, I take all of those forces, I add up their vectors, and I get the net force. The net force is another vector, so that means it's going to have x and y components. But that net force will produce my acceleration. So if we've been asking about where have these accelerations been coming from, whether that's an x acceleration, a y acceleration, some in between like an acceleration on a slope or anything else like that, they have been coming from forces. But today is the day we start to look at those forces that are actually going to create the accelerations that we're so used to dealing with now. The unit, while we're talking about these things, the unit of force is a kilogram meter per second squared, which is a mouthful to say, so instead we just call it 1 Newton. Right? Again, if you do a bunch of stuff in science, then you get stuff named after you. That's just kind of the way it goes. So, I've got something for you here. This is not necessarily a net force, maybe in a little bit of a sense here. But we have force measured in units of rubber bands, and I assure you that all of the rubber bands are completely identical. I also have a graph of as more forces apply to 3 different objects, their accelerations mapped out with this strange A1, units of A1, whatever that is. I will tell you that object 2 has a mass of 0.2 kilograms. That is this central slope right here. That has a mass of 0.2 kilograms. What are the masses of objects 1 and 3 based off of this graph? I'm going to give you guys about 4 or so minutes to work on this one, and then we'll take a look at it together. Okay, so I think we should probably go ahead and get started with this one as we've got it here. So here's what we've got, right? I have thrown something at you and I have said, hey, would you look at this brand new fancy equation that would tell us about accelerations if only we had all of these discrete values? And then I immediately gave you a graph that is very clearly not a lot of discrete values. Okay, we need to figure out some way to actually work with this. But what I'm going to do is I'm going to start by writing down this equation that I've got, and let's think about what we can do with this. So we start with our F is equal to ma, and that's fine, but I'm going to rearrange this just a little bit. Let me move it over to the other side. Let me say A is equal to F over m. Better yet, let me write this out as 1 over m times F. Now, it seems like I'm just kind of unsimplifying this problem, but if we think about this thing, this looks quite a lot like a slope-intercept kind of form of an equation. It's a linear equation that we could be relating together here, where A is our y-axis, F is our x-axis, and then whatever shows up in this middle here, B, the slope of our function. So we're going to have 3 of these in total, one for object 1, object 2, object 3, where our slope, whoops, let me make that a little bit more look like a B. Our slope is the inverse of the mass. So let's start with object 1. Let's take a look at that thing. If I look at this point right here, let me take the slope of this thing, and I'm going to say, okay, well, my rise over run is going to be 5a1 divided by 2 rubber bands, which I assure you is a standard unit. Right? Shows up in a table somewhere, I'm positive. This standard rubber band force, but whatever. So that's fantastic. That would tell us what our mass would be. The slope should equal the inverse of the mass. B is equal to 1 over m. Except, what is A1? I don't know. What we have to do here is we have to actually go to the only other object that we actually know. Object 2 is going to be essentially our calibrator for this graph. That's going to relate these values together. So I look at these things and I look at path 2, and my slope for object 2, this one in black, our slope for object 2 is essentially 1 rubber band, or 1 A1 per rubber band. Right? That is to say, if I'm expecting my slope to be A1, then that should equal 1 over the mass that I'm given, 1 over 0.2. A1 is equal to 5. So when I come back to my object 1 then, I say, okay, well, now I know what A1 is equal to. A1 is equal to 5, so what I've actually got right here is 25 over 2 is equal to the mass. Let's flip it all. 2 over 25 is equal to the mass. The mass of object 1 should be something like 0.08 kilograms. I can go through the same process. How did I get the 0.2 up here? That is one of my given values. That is, the mass of object 2 is 0.2 kilograms. Yeah, so that's what I needed. Otherwise, I can talk about the relative masses, but the fact that I actually have one of the values means that I can use that to find what the other should be. So let's keep going with it. Let's say object 3, because we already know what object 2 is. And object 3, this is not a good spot, right? So I'm going to go a little bit before that. I'm going to look at this spot right here. At this point, my rise is 2 times A1, 10, over 5 rubber bands. Should be equal to 1 over mass. My mass should be 0.5 kilograms for object 3. Well, let's keep cruising along then. So, Newton's first law. You might have seen these things, right? There are 3 in total, and we have technically already seen the second one. But there are 3 in total, but I do want to state these things out while we're here. And we'll kind of carry this idea for a little while. But Newton's first law, translated into a modern understandable definition, is that an object that is at rest will remain at rest, or an object that is moving will continue moving in a straight line with a constant velocity if and only if there is 0 net force acting on it. So, an object at rest stays at rest. Somebody has to push or pull or do something to that object to change that. If an object is already moving, it's going to keep moving just like it is unless somebody pushes or pulls on that object and changes its movement. You can't change the motion of something unless you act on it with a force. That is to say, this book right here is not just going to spontaneously fly off of my desk. I have to do that myself. Right? There's a bit of manual labor involved with flipping the table after a particularly upsetting game. The table will not flip itself. And that's, in a sense, described by Newton's first law. If you want the actual quote from him, it is every body perseveres in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed thereon. Newton was historically one of those, while you were out partying and drinking, I was in my room studying the force kind of stuff the entire time, if anybody actually gets that joke. He was kind of a shut-in. He didn't really like other people. He just wanted to stay in his room and work on physics all day, every day. And actually, when he came up with a lot of this stuff, he had a really great opportunity to do so because he was in a pandemic. There was a pandemic sweeping across Europe at the time when he was doing a lot of this work. So, I think that was actually specifically when he derived calculus. So, you know, derive some calculus. We've got some time still. You know, there's another month or two. But yeah, I think that definition's a little bit convoluted in language nowadays. So I like this one that's a little bit boxed in. That works a little bit better for myself. So with that in mind, though, think about this. We've got a concept check here. We've got like 3/4 of one of those like cat toys where the ball's stuck in the track or something. But essentially what's going on here is I've got this ball and I'm going to launch it through this tube, and it's going to wrap all the way around the tube, and then right here it ends. Comes to a sudden end. There's no more tube. Of those 3 paths, which one do I most expect the ball to take? What do we think? A, B, or C? Okay, I see a little bit of a variety in answers here. Ooh, a CB, covering both bases on that one. Impressive. So, let's think about it. And let's kind of think about what actually goes into turning this thing in the first place. When this thing starts moving, if we actually think about what controls the movement of this thing, does the inner wall do anything here? If I'm being honest, not really. Right? Imagine you are ice skating or roller skating and you're doing it in a rink and you're not very good. To the point that you're kind of hugging the wall the entire time. If you're hugging the wall the entire time, if your shoulder's pressed up against the wall, you don't really need to worry about turning yourself, do you? You'll just glide along the wall, and then you're on your straightaway again, then you'll kind of glide along the wall. In the same way, if anybody knows those high-speed race tracks, it's a big straightaway, and then it turns into a curve, a 180-degree curve, but it kind of banks up at an angle, right? The reason for that is what's actually compelling the ball to change its direction is this outer wall right here. This outer wall says, nope, you're not going this way. Nope, you're not going this way. And it kind of does that all the way along, guiding the ball the entire time until we get right here, our final spot. And our very final spot, there's no more outer wall to redirect the ball. At that moment in time, right before it left, it was going up. Now there's no outer wall to change that direction anymore. So it's going to continue going up. There are no forces, no objects, no collisions, or anything else that would force it to go along the paths of A or B. It's going to continue going in that straightaway path. Right? If anybody had played Roller Coaster Tycoon or anything else, when you have a sharp turn or a steep hill or anything, right? When you launch them off, they don't suddenly like curve with the rest of the track. They're off the track at that point. There's no forces to keep them going along the track that was set out. Well, they're flying into a cliff at this point. So let's keep looking then. So for a lot of these things, if you have not been drawing pictures, now it is very important to do so. And it was important to draw pictures before, so it's doubly important now. A free body diagram is what we use to organize all of our thoughts and our descriptions of what is happening to an object. So I don't necessarily go along with the order of these things. I do these a little bit different myself, but this is not a bad strategy. I like to think of this in mostly 3 steps, maybe 4, depending on what's going on. I draw a picture. If I have a block, I will draw a block. Then I will go through piece by piece and I will think about every single force acting on that block. Maybe I have a force of gravity. Maybe I have a force of tension. Maybe I have a normal force. Maybe I have a friction force. For every single one of those, I'm going to draw that vector and label it on my picture. Once I have done that, I will think about the axes that I would like to choose for this problem. So perhaps for this one, I'll go with the standard. I'll say y is up, x is to the right. There might be reasons to change that though. Depending on what I've got in my picture, I might decide to rotate it, I might decide to flip it, I might decide to do anything with it. I think it's a little bit easier to draw out the forces before I start to draw out my axes, though. I think that's one big thing I have on this one. In the book, it's recommended to think about the forces first and then draw them on later. I like to draw them while I'm thinking about them. That just works a little bit better for me. But then we want to have the vectors on each of the forces. We want to have an idea of what each of these are. We will generally try to represent the direction that we think the forces are going on our picture, and that helps us organize these things into X, Y, Z, whatever directions we need. Finally, and this last one is very optional, it's to, if you know what it is already, you can try to draw and label the net force on the object. I don't think that's a very common thing to do, just because most of the time I really don't know what the net force is necessarily doing. Sometimes I do, but not always. So, but in total, you will find kind of your strategy for how you want to draw out free body diagrams and organize all of your thoughts, but you do absolutely need to draw out free body diagrams. So, some of these forces that you might be considering, 2 of the really common ones, I know there's a huge long list of them in the book, but 2 of the most common ones are going to be weight, that is the force from gravity pulling us downwards, and the normal force. And the normal force is a lot of things. I set my arms on my desk. There's a normal force pushing up on them. I push against the wall. The wall is pushing back on me with a normal force. I'm sitting on my chair of sorts. That chair is pushing back up on me with a normal force. The normal force is any time 2 objects are touching up against each other, trying to move within each other's space, and there is a perpendicular force, perpendicular to that surface, pushing back out against it. That is to say, imagine here that the normal force didn't exist in all scenarios. I cook my dinner, I plate it, I'm ready to eat. I try to set the plate down on my table. The table doesn't provide a normal force. My plate and my food phase through the table. That doesn't happen very often, right? I've never seen it myself. I would probably not believe you if anybody told me that they had seen that. The normal force is what stops two objects from phasing into each other, right? Generally speaking, I'm not just going to go through this wall, not unless I punch a hole through it or something, but that's a different story. If I'm pressing up against the wall, my hand is not just going to suddenly seep into it. There's a force that the wall is exerting, keeping me out. That is exactly what the normal force is. I don't know if it's called the normal force because it is always a common force that we see everywhere, or if because it's literally what we would call normal to the surface. Normal means perpendicular. I don't know why. It feels like confusing language to me. I'm used to it by now, but if you ever see something that is normal to something else, that means perpendicular. But this is an example of a free body diagram of somebody that's standing in place, right? Gravity's pulling down on them, but they're standing on the floor. They're not just falling through the floor. The floor pushes back up on them, keeping them in place. So there is weight, there is normal force. Once we have both of those things, we can label our axis. Is the force of gravity equivalent to the normal force pushing back? Sometimes, but not always. So, and this is kind of a fun thing. There are some nuances to the normal force that we will begin to explore a little bit more, but you can imagine here that the normal force is only as much as needed. Let me just, so you can actually see me pushing against the wall here. There we go, my hand's on the wall. The normal force, as I'm pushing with this thing, if I'm pushing just a little bit, the wall just has to push a little bit back, right? The wall doesn't have to exert a lot of force to keep me out. If I really start to lean into it, if I put more and more force into this thing, and I think there's a stud nearby, so I'm not going to go through it. But if I really start to push into this thing, the wall has to provide more and more force to keep me out. So that's why tangentially related to is the normal force equivalent to gravity, because sometimes there might be more than one normal force. There might be a few different things happening all together at once. It depends on the problem, depends on what's happening. So I want you to get a little bit of practice at this one first. Let's imagine here, we've got a scenario. An ice hockey puck glides across frictionless ice. No friction force. Draw a picture, define the reference frame, that is the axes, X and Y. Draw a free body diagram and label the forces that are going to be acting upon this thing. I'm going to give you just about 2 or 3 minutes. And then I can't look at your picture. We can't confirm numbers or anything else. Everybody's picture is going to be a little bit different, but we can see if we've got something at least kind of similar. But let's go ahead and draw a picture. And I know the descriptions of this always say to draw like a dot for the mass for the object. I don't like to do that. I think it kind of pulls me out of actually what I'm doing in the problem. If I'm just drawing a dot and drawing a bunch of arrows on that, I don't necessarily connect my thoughts very well to that. So what I'll do for a lot of these is I'll actually draw the physical object and then I'll just draw the forces acting on it from there. So let's go even so far as to draw something like the ice that it's on, and these little lines right here tells me, hey, this is like the ground. This is something solid that I can't pass through. It's not just empty space. We have a hockey puck. I'm sure that is up to the standard of what gets used in competitive play. So think about all the forces that might be acting on this. And first of all, we of course know we have been seeing all sorts of projectile motion, and we know that we are on Earth doing this. We expect that there is going to be some sort of gravitational force pulling us down. Let me start with that. F of G, force of gravity, pulling us downwards. And I know some of the different places, there's a little bit of discrepancy here of whether you want to call weight like a lowercase w, a capital W. Some people will draw this as just mg. I personally like to use F of G. I like to label most of my forces with F first. Tension's kind of like an exception to that. Normal force, similarly, lowercase n, capital N. I use F of n. Just, it's what I'm used to. It's the standard that I like to use. If you find something different that works very well for you, fantastic. You're welcome to, yeah. Whatever you want to do for that. So, as we've got this thing, we know that there is a force of gravity pulling down. However, I don't imagine that the hockey puck is just going to slide into the ice, right? I'm imagining we're kind of skating across instead of just going into the ice. So that tells me that there must be something repelling the hockey puck, stopping it from moving downwards. That, of course, would be a normal force. The normal force from the ice stops us from falling into the ice. The last thing that I'm going to do on this one, and this is not something that's necessarily standard, or I would even imagine some people, some other professors would probably discourage this actually. I do want to draw out my axes for these things, but the last thing that I like to do for some of these is I do like to draw out, if I have other information, like the velocity or an acceleration or something else like that, I do like to label those things. I think that helps me understand what's going on a little bit better. I've got a quick reference right there. So for the hockey puck like this, what I would do is I would draw like a dotted line, a dotted vector. Call this my velocity. And the fact that it's dotted now tells me, hey, this is not like the other ones, right? All of the forces are solid lines. So if you see something that's dotted, it doesn't fit with the rest of them. But it does give me a little bit more insight as to what's going on in the problem. Now, if this thing is sliding across frictionless ice, do we expect it to have any sort of change to its velocity? Is there any acceleration on this thing? What do we think? No, I wouldn't think so. I mean, in reality, there might be a little bit of friction, but ice is pretty slippery. We can almost get away with saying that there's not going to be any friction. So I would expect this would probably be a constant velocity as long as this thing was moving, right? As long as we're ignoring whatever little tiny bit of friction there actually would be. So let's try to wrap this into the next problem. We're going to draw another picture here, but it's a little bit more of a complicated scenario. Let's imagine you are doing your tour driving through Australia or something, and Kangaroo Jack himself jumps in front of the road, or jumps in front of your car on the road. You recognize, of course, he's wearing his characteristic red hoodie and sunglasses. There's no doubt in your mind who it is. You slam on the brakes as fast as you can, but you're going down a 20-degree incline. Draw a picture, define your axes, and draw the free body diagram, everything as you see fit in this picture. See what you can come up with on this one. I am looking for more forces than I just saw, right? So at least 3. Whether it's more than that, I won't say quite yet. Consider all the different forces that might be acting here. Draw them, label them, have as many details on your picture as you can that you think is going to be helpful and useful. I'm going to say take the next 4 or 5 minutes on this one. And then we'll take a look and we'll compare pictures, and I'll talk about what I've got and why. But 4 or 5 minutes, and then we'll come back and check. Okay, so let's go ahead and start drawing this thing out, and we want to be as accurate as possible here, and include as many memes and jokes in one picture as we possibly can. So actually, let me go ahead and get a new page for this one. Let's go ahead. Let's start with our slope. So I'm going to draw a straight line for where I would expect level ground to be, and that's just kind of a reference point for me here. From there, we know that we're on some sort of 20-degree incline, something like this. So I'm going to call this, we can call this 20 degrees for now, but I'm also just going to label this as theta. I think that'll help out. Now, get something somewhat flat that I can draw on. We'll go ahead and include, of course, if we're driving through Australia for some random reason, I assume that we're driving Cybertruck. So something like this. And the blockier it looks, the more accurate it actually seems to be for what Cybertruck actually is. Because There's a limit to the number of things that are actually backwards in Australia. So let's think about all these different forces. And I'm going to start with the obvious one. We are still on Earth. Gravity still pulls towards the ground, just like this, F of G. And real fast, before we get too deep into these other things, I do want to think about what's going on. Let's go ahead and, the reason that we're slamming on the brakes, that's probably not a very fantastic start. Something like this, something like this. A very poor representation of what a kangaroo looks like, because again, I don't actually live in Australia. Something like that kind of looks like a kangaroo. And we'll put some shades on them so we know it's Kangaroo Jack. So, as we've got this thing, we're trying to slam on our brakes, but right now, we're already moving, right? We were moving forward when we started this thing, so we should have some sort of velocity that's going roughly in this direction, I would think. And again, I'm doing this as a dotted line, a dotted vector, because I want to imply that this is not a force. This is my velocity. My velocity is going this way, and this gives me a little bit of a reference for some of these other values. But the dotted line and the fact that it's not actually connected says, hey, don't confuse this with the other things. This is not a force. Okay. The other two things that we've got. We are making contact with the slope. We are making contact with the ground. There is a normal force that the ground is exerting on the truck. That is going to be perpendicular to the ground, though. So it's not going to be pointing straight up to counteract gravity. That's not it. It's going to be pointing perpendicularly from the slope, like this. So there's my normal force. And the last thing that we've got that I'm going to consider at least is we are braking. And think about what happens anytime you slam on the brakes in a car, right? And you're not trying to like really slam on them, but anytime you press on the brakes in your car, it doesn't matter if you're going north, south, east, west, up a slope, down a slope, turning, whatever you're doing, your brakes are always trying to slow you down, to decelerate the car. That is, it's always pointing against your velocity. So when we slam on the brakes, I expect that the force from the brakes points in this direction, against my current velocity. And that's another reason that I like to include that velocity, because that gives me a sense of direction for things that might be related to the velocity. So these are the three big forces that I might consider here. Now, who likes to deal with everything, breaking it up into X and Y components every single time, versus just lining it up along the X or the Y axis? Does anybody really love components so much that they wish every single vector could have X, Y, and Z components? I would guess not. Personally, I wouldn't want to, and I would think that I've been doing this long enough that if that was going to set in, it would have happened by now. I don't particularly care for having a whole bunch of vectors that have components in every single direction. So what I see right now is kind of a hodgepodge of directions, right? These are all kind of at angles with each other. There's not like one unified direction for all of my values. But if I know that Y and X have to be perpendicular to each other, if I draw out something like this, then gravity points along the Y-axis, but the brake force, the normal force, and the velocity are all going in both X and Y, which makes this a rather complicated problem to solve. If instead I was clever and I thought, maybe I pick different axes. Maybe I think about something else that, some other way that I could arrange all of my forces that would still get the job done, but might make this a little bit easier. And the best way that I would imagine this is to label Y coming like this, and X to be going down the slope. Now, my normal force points in the Y direction, my brake force is in the negative X direction, my velocity is in the positive X direction, gravity's the only one that doesn't fit. So I've got three vectors that line up along my axes though, and I think I'm going to take that over the one. I think that's the better deal to take in this case. So, as we've got this thing, now we need to think about this in such a way, this is a complete picture, this all seems fine by me. But I do want to talk about how I would actually deal with this now, because you're going to be faced with a lot of problems where you're going to have to do something like this. Specifically, I need to think about how does f of g actually break up into my x and y directions. Here's what I'm going to do. I'm going to continue that y-axis downwards like this. And let's make it a dotted line so again we know, hey, this is not a force, this is not anything else, this is like a reference point. I know, if I do a little bit of geometry here, let me draw another dotted line right here. This is a right angle. This is a right angle. This angle right here must be 70 degrees. So this one must be theta. Let me draw that a little bit more zoomed in. Let me focus in on that triangle because that picture's getting a bit complicated already. I've got this, I've got this, I've got this, and I'll have something that is kind of perpendicular to it. Okay, I've tried to draw this in such a way. Here's a right angle. Here's another right angle. If I take this angle theta, and I call this angle right here, so from the slope out to this vertical line, not all the way across, I know, and let me label this thing phi. So I know theta plus phi plus 90 degrees, this whole thing is a triangle, this should equal 180 degrees, right? That is the total sum of the inner angles of every single triangle. Must be true. That is to say, theta plus phi is equal to 90. If I know that I have a right angle right here, that's 90 minus phi should give me theta. That's how I solve that one out. Now, I think about what happens when I actually want to break that thing up. This is a complicated picture in its own right, so I'm going to erase some of these details for now. Let me get rid of that. Let's kind of hide some of these things and make it a little bit easier for us to read. So that's my angle theta, and I'm going to get rid of the, let's get rid of that too. Clean it up just a little bit. I need to think about the x and the y components of this gravity now. So what I'm going to do, let's do this in blue so it stands out just a little bit better. Here is my y component of the gravity. Make it even a little bit thicker here. Y component of the gravity, x component of the gravity. We'll label those. I'll call it FGY and FGX. FGY, FGX. Now that I have these, how am I going to break them up? What is the x component of the gravity? It's going to be FG sine or cosine. What do we think? I would agree. Sine should be the one here. Sine of theta is the one that I'm expecting to see. Because if I'm just looking at this triangle, SOHCAHTOA says sine goes with the opposite over hypotenuse. Opposite in this case, opposite from the angle, is FG of x, not FG of y. So when I was giving those warnings out about sine does not always go with y, cosine does not always go with x, this is one of those cases, and we are going to see this very often. So keep that in mind. Kind of going off of that, FG of y would be FG cosine of theta. Now, one of the ways that I have to check on this one, if all that you remember is this is a little bit weird, whatever this case was, I remember that the x isn't necessarily cosine, but I don't remember y or whatever else that happens with that. Here's my check for this. I imagine what would happen if theta went to 0. If my angle, if my slope went all the way back down to level ground, what axis would I expect all of gravity to be pulling in? What do we think? Y. Yeah, I would agree with that. It would be just pulling straight down again. I wouldn't expect anything else. If I was on level ground like this and I called y pointing up, gravity pulls me straight down to negative y. So when I start to increase that slope, when everything starts to tilt just a little bit, gravity's still pulling down, the force going in the y direction in my tilt gets less and less and less and less and less. It matches with my cosine of theta. When I plug in theta is equal to 0, all of the force goes in the y direction. none of the force would have gone in the x direction. It's not until I start tilting that I actually see some force start to leak into the x direction. And then we look at this thing a little bit closer, and we say, hey, fg of x, fg sine of theta, if you have done a little bit of the reading now, fg is most commonly m times g, the mass times the acceleration from gravity, 9.8, which is part of the reason why we use positive 9.8. If you plug that in, then what you realize is this force from gravity in the x direction, a of x, is g sine of theta, exactly the acceleration term that we gave you when you had something going down a slope. It all ties back together. I remember when I said that to you, I said that I'm just going to give you this thing. You've got to trust me for now, but later on we'll prove it. Here's the proof. This is where that actually comes from. When we start to involve other forces, that might fall apart. But when gravity is the only thing acting on it, we can recreate our g sine of theta being our acceleration down the slope. So I can hear the collective mind blowing from here, but do we have any questions on what we see here? The normal force is kind of, I think about the normal force like a reactive force. The normal force is not there unless something is making it be there. Because, like, if I'm pushing on the wall or anything else, right? Again, in this case, if I'm only doing a little bit of pushing, the normal force that the wall needs to exert back on me is not that great. If I push more, the normal force from the wall has to increase. It is reactive to what I'm doing. So when the car is going down the slope, as that slope increases, the normal force that needs to counteract gravity goes down. But for example, if we took some, like, water jugs or some bricks and we laid them in the back of the truck, now the truck's going to be a little bit heavier. The normal force has to increase to compensate for the fact that there's more forces pulling down. Or more forces pulling into the slope is what I should say on that one. So, I want to keep moving on a little bit for now, because that is most of Chapter 5 all kind of covered right there. Right, so now we move on to what do we actually do with these things, right? We have just been drawing some fancy pictures. I have shown you how to split up some things, and even that is kind of like a hint as to what's going on. Forces are not the entire thing of it. Dynamics are what we use to talk about how those forces cause accelerations, cause movements that we can use our good old classic kinematic equations to solve for. So, this slide again. Right? We know what forces are. We've seen some examples of forces. We know how to draw forces on different pictures. So all of our old kinematic equations, we most of the time had to have some starting information like position and maybe initial velocity and the accelerations. Now we're going one step extracted from that. Oftentimes now we will need to find the acceleration because of forces acting on our object. Forces cause acceleration, cause change of velocity, cause change of position. Right? It's just an extra step that's been added here. Most of the time, we are going to label this in such a way where we would have acceleration is equal to F net divided by the mass, m. And the reason that both of those have vectors is because, just like with everything else in kinematics, we can split up the x and the y components, and they will behave completely independently. Time will tie them together, nothing else. Right? They might share some variables in different places and everything else, but if there's a bunch of forces going on in the x direction, they don't have any impact on what's going on in the y direction. So, let's imagine a common scenario that we will see oftentimes is going to be the case of an object being in equilibrium. Equilibrium, generally speaking, means no net forces. There can be a lot of forces. It doesn't have to be no forces. It can be a lot of forces. But all of them sum up so that the final net force vector is equal to 0 in both x and in y. There are two possible cases because of that. Either you are at what is called a static equilibrium, where static means stationary or still or stalwart in your position or other ST words that mean not moving. Static equilibrium is the scenario where you have zero speed, zero velocity, no movement at all. You are at rest. Forces might be acting on you, but there's no acceleration because of them. Dynamic equilibrium is a body moving will continue moving. You have a velocity. It is a constant velocity. there is no acceleration. Is circular motion a dynamic equilibrium? Yes or no? What do we think? No, it is not. There is a radial acceleration in circular motion. Circular motion has a constantly changing velocity, so it would not be considered dynamic equilibrium. So, here is a rough timeline of how you can approach a lot of these problems with forces. I sometimes mix up some of these steps and everything else, but if you want to organize them, this is what usually gets recommended. First, as always, is to draw a picture, and I will do that no matter what. I will draw a picture to begin with. I will set the stage for what I'm about to do. Next, I will start thinking about all of the variables that I've got. Oftentimes, I will put them in a nice little list of all of my given variables, all of the variables that I'm interested in finding. Oftentimes, I will start to mix in this step right here. I'll start to think about what forces are acting, which forces of these are my given variables, and I'll start to draw those on my picture. I usually like to draw the axes after I have put my forces on the picture, but you might decide to do it sooner than that. It doesn't matter a ton. Drawing the axes, drawing the forces, all of that stuff, very, very, very important to do. Make sure you do both of them. Then I start to think about the forces going in each direction. That is, I split up all of my forces in the x direction, I split up all of my forces in the y direction, and I treat them separately. I do the rest of my physics, which is generally writing down any equations that I might need. I do the rest of my math, which is typically a lot of algebra and a little bit of number crunching. And then, of course, we keep the party going, we keep having fun, we keep crunching through new problems. So, let's try it out. Let's imagine I have a very light metal ring right here in the middle. So light, in fact, that the force of gravity pulling on it is negligible. It's too small for me to care about. Attached to that ring are 3 ropes. Remember that ropes pull with a tension force. So I have rope 1, I have rope 2, and then what I could call rope 3 is pulling with 100 newtons, 30 degrees below the positive x-axis. Draw this picture out. Please, draw this picture out. Draw your axes, draw your forces. Once you have done that, separate out x and y directions, find T1 and T2, the tension in rope 1 and rope 2, the magnitude of each tension. So, I'm going to give you guys, say, the next 4 or 5 minutes here to work on this one, and then we will talk about it all together. Okay, let's start taking a look here. So, I want to draw this thing out for myself to start, right? Let's get a lesson in drawing fantastic pictures. I mean, we've already had one of the best, but what could a second lesson also do for us here? So, let's draw this thing out, kind of roughly what we saw in the picture there. And what I like to do for some of these things, you might have noticed this when I was drawing the ice, but for some solid objects or something else, if I want to distinguish, is this open space, is this open space, I don't know. I'll draw like these kind of, I don't know, surface lines, something like that, to say, hey, this is a surface that we're actually looking at here, right? This is not nothing. Now, we have maybe, if you squint your eyes a little bit, it makes it a little bit more obvious that this is our open space. So, I'm going to draw a tiny little ring attached to 3 different ropes. So I've got one rope pulling up like this. I have one rope pulling over like this, and I have one rope pulling out at an angle like this. So what we can do is we can say, okay, well then every rope is going to be pulling with a tension. That's what ropes do, right? Ropes don't ever push. They fall slack at that point. You really can't push with a rope. You have to pull. So for this brass ring, I know that each rope is pulling, and it's going to be pulling away from the ring where it's attached. Call this one T2 because this, in my picture, is rope 2. then this right here is going to be T1. And just for the sake of it, I'm going to call this one T3. Let's just give them all names. They're all 3 tensions. What I'm also going to do while I'm here is I'm going to draw out a horizontal because that was in the picture and it's a pretty good thing to have. So a dotted line to say, hey, this isn't anything but like a little reference point. I have this angle right here, 30 degrees. Call it theta. And while I'm at it, let me also say 100 newtons. That's my tension. If I hold shift when I draw lines, it'll make them perpendicular. Oh, no, that does a very different thing on this one. I don't know if you use Krita or not. This is supposed to be professional drawing program, semi-professional drawing program. One that I am not equipped to use, but it's got a lot of weird hotkeys and everything else that I'm not used to. So we have our picture. Let me go ahead and label some axes. I don't see anything crazy in this one, right? I've got 2 vectors that are already pointing along what I would be calling my standard X and Y. I have an angle coming off of the only one that is non-standard. I'm just going to go ahead and use my common Y and X. My common Y and X here. And that means, let me go ahead and write out my given variables so I can organize all my thoughts here. I know that T3 is equal to 100 newtons. I know that theta is equal to 30 degrees. I know one other key piece of information that was not explicitly given, but what is it? What other variable do I have, do I know to be true in this case? What do we think? Not gravity. Remember, we said very, very light. Very, very light means gravity is not a big deal here. Sum of all forces is 0. That's the key that I'm looking for. I could say that all of the forces in the x direction would be equal to all of the forces summed up in the y direction, because both of those should be equal to 0. And I want to make another point here. We don't have any normal forces in this picture. There are no normal forces here. Because again, ropes do not push, they only pull. So there's not any sort of normal force to counteract because there's not contact, there's not 2 objects pressing up against each other in the same way. It's ropes just pulling on the ring. So, with this in mind, what I'm going to do is I'm going to make my life a little bit easier here, and I'm going to split up my third tension into its x and y components. This one is a standard one. T3x, tension in the x direction, is going to be 100 times cosine of 30, which I should get to be 86.6 newtons. The y component should be T3 sine of 30, should be something like 50 newtons. With those two out of the way, now I can look, let me go ahead and write out my, let me finish my variables here. I'm asked to find T1 and T2. So what I will do now is I can look at this thing and I can say, okay, well, let me start with the x direction. All of the forces in the x direction should sum up to be equal to 0. What actually goes into the x direction? Well, I have the x component of T3 pointing in positive x. I have all of T1 going in negative x. All of that should sum up to be equal to 0. 86.6 minus something is equal to 0. T1 is equal to 86.6. How do we feel on that so far? Now we can do exactly the same thing for the y direction. I could say that f of y, everything in the y direction should be 0. I don't see this ring moving anywhere. F of y should be equal to 0. T2 is pulling me up. T3y is pulling down. Something minus 50 is equal to 0. I would argue that it's probably 50 minus 50 is equal to 0. T2 should be 50 newtons. T1 equals 86.6 because it needs to counteract the pull from rope 3. Rope 3 pulls in both the x and y directions, so T1 is responsible for canceling out that x component. T2 is responsible for canceling out that y component. Does that make sense? Perfect. Okay, so I do have a concept check, though. We said it was very, 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 very light. Light enough that gravity was not a big deal. What if instead we had made this ring out of like uranium-238? So despite the fact that it was small, it was still very heavy. How much would change? Let's start with our picture. What would now change in our picture? But what would change? What changes in our picture here? Not drag. Drag is something that's very different. That drag requires movement. But I would expect then to actually not neglect the fact that I have a gravity force. Gravity certainly would apply then. If gravity applies, that's only pointing in the y direction. So the x direction doesn't actually change. There's no difference to what we had there. But if we look at our y equation, we have this extra term, f of g, pulling downwards, which means our final result for T2 would just increase by whatever that weight would be. Tension 2 would have to counteract a little bit more pulling down on the ring, so the tension in it would just increase a little bit. If we had to consider the weight of the rope, it would be pulling down towards the middle of it. So if we were thinking about like what forces are acting on T1, or on rope 1, I should say, that if there were to be a gravitational force, it would pull down right here. And the other end, the way that it would be attached to the wall, would pull up a little bit, and then over on the ring would also pull up a little bit. It would split where it was going. There's some different things on that, but you would most easily consider, you always consider the mass to be pulling down at the center of the object, which is actually something that I can get to right now. So, speaking of these things, all of these things that we've been assuming so far is that when we're working with free body diagrams, they even say it in the description here, and I don't necessarily agree with it, but where did that slide go? There it is. Represent the object as a dot. I don't like that. I am personally not a big fan of that because I think it kind of depersonalizes, isn't exactly the word I should go for, but it kind of depersonalizes the problem for me. If it's not a block or a puck or Cybertruck or whatever it is, if I'm just drawing a dot for every single problem, then when I'm looking at what I've got, it kind of abstracts it a little bit too much for me to think about what's really going on. I like to draw the object myself. If you prefer to draw the dot, more power to you, right? I'm sure that there are plenty of people that would agree that's the way that it should be done. That's the proper way. I'm not a big fan of it. I like to draw the object, and I like to draw the forces acting on the object. It just works a little bit better for me. But the dot is what they recommend. And the reason for that is because most of these objects, as we're acting on them, we're not thinking about the fact that these are real objects that take up some space and have a mass density and a distribution of mass, and gravity is going to be pulling on all of those different, intrinsic atoms of the object. Instead, we think it's one thing, one point mass, as we call it, and all of the forces are acting on that point mass. And of course, doing that is not the most accurate, the most complete picture. However, doing that is incredibly close to what actually would be happening, to the point where why would you add all of the complication to actually consider the mass distribution of the object if you could simply say it's all acting right here and call it a day. Get 99.9% of the way there with that assumption. It works much better. It's a much easier thing to do. it's not until we start to have forces acting on different parts of the object that we're going to have to consider this. If I took this pen or anything else and I applied a force right here, it doesn't necessarily go up, it spins. And that's a very different beast. We will tackle that soon, but it's not quite what we're looking at yet. For now, it's blocks and other things that do not spin. It's things that we can treat as if they are point masses and work from there. So I've got one last problem for you here. This one, I have already given you the free body diagram. There are 3 forces acting on this black dot right in the middle, right? And we're really hammering home. This is a point mass, and it's quite literally a point with mass. 3 forces acting on it, and we have been so kind that even one of the forces, we have already broken it into components for you. So what I want you to do, though, if that point has 2 kilograms of mass, what is the net acceleration of the point? I'm going to give you just 4 or 5 minutes, and then we'll take a look at it together, and that'll be the last thing we do today. All right, let's take a look here. So we've already got the picture drawn out for us. So there's really not a lot to do on that one. There's not any extra forces that we're expecting to see. There's no mystery surprises or anything else like that to pop up. Take the picture exactly as it comes. Now, so at some point or another, my program changed how I'm allowed to copy things over, and it copies things over as vectors. And again, this is technically a more professional drawing program, and I am certainly not qualified to be using it properly. So I'm going to have to draw this one out manually real fast. Hope you don't mind, but we can talk through these things. We have this one going down by 3. We have this one going over by 2. Let's go ahead and draw these things out as we see them. As we see them. We are also given that we've got this diagonal one, and we would have to solve out for this thing, except we are already told that the components of this are 3 and 4. Label all of it. 3, 4, 3, and 2. So when I consider all of that stuff together, I need to look individually at each component. I need to look at the x component, and that means f of x. What does that equal to? Well, I see a positive 2 and a negative 4. For a net force in the x direction only of negative 2 newtons, that alone is not acceleration, though, and I cannot just say that means negative 2 meters per second squared. What I have to do is I have to say, hey, this object that I actually have in the middle has a mass of 2 kilograms. I know that F is equal to ma, or A of x is equal to F of x divided by m. Negative 2 divided by the 2 kilograms should give me a net acceleration in the x direction of negative 1 meters per second squared. I look at the y direction. In the y direction, I have a plus 3. I have a minus 3. That's 0. 0 newtons, 0 acceleration. A of y is equal to 0. And I would be happy with that right there. We could also say that the acceleration vector is equal to negative 1 I hat meters per second squared. 0 j hat, if you want to be very, very thorough with it. How do we feel? Agree? Disagree? Well, if there's nothing else, why does the sine and cosine theta come into play with a diagonal force? Sine and cosine theta always have to show up when you have to break things into the components, right? If it's not lying along one of the axes, if it's not lying along the x or the y axis, if it's pointing somewhere in between, then you need to split that vector into its x and y components so that you can actually deal with it with the other vectors. That's true for velocity, for acceleration, for forces. Anytime you've got a vector like that, if it's not pointing along one of your axes, then you're going to have to break it up into its components. But I think right now, I'm going to call it at that for the end of the lecture. And next time, we'll be back talking about some more forces.